have a guest speaker, Dr. Frauke Kracke from Stripe Climate and Frontier. She's a science lead. Actually, she studied the biotechnology and obtained a PhD from University of Queensland in 2018, and then moved to Stanford as a postdoc and then staff until 2022. And then from 2022, I think she is leading this position. And I think Stripe's contribution to the carbon credit market is very significant. And we are very much interested in learning from this whole process, a little bit away from the science, but I think we will see a lot of also science as well. So, Frauke, thank you for agreeing with us to join the lecture. And now I will stop the sharing the slide. And just for the general audience, so we are recording this video, so be aware of it. And Frauke, please take the screen, microphone, and video everything from me. Yes, thank you.
Great. Thank you. Thanks for the nice introduction, and hello, everyone. You can see the screen okay, right? Do I have the right one up?
Yes.
Perfect. Great. So it's a pleasure to be here. I'm a scientist by training, as Jung pointed out, but today I'm going to give a little bit more of a high-level overview of the work that we're doing at Frontier around to advance carbon removal solutions. Give some examples about like technologies that can remove carbon from the atmosphere and are doing so today already. And then share, given that this is like a very sciencey audience and carbon removal is a very early field, there is plenty of knowledge gaps to fill in the field. So I'm going to highlight a few of those, and then hopefully we can have a bit of a discussion on what's like most important or interesting to people here. Okay, so I want to start, reminding us all of the challenge, because when we think about carbon removal and also just like a reminder, given that CORC is like working on a multitude for carbon solutions, including utilization, emission reduction, and like all these super important technologies, our work is focused on carbon removal only. So that's like net negative solutions. So any technology that like leads to a reduction of CO2 in the atmosphere, right? So when we talk about carbon removal, that's what I mean. And just want to start with a reminder of this challenge and the sheer scale of it, which is kind of scary, but it's very healthy to constantly keep reminding of that. So like any solution that we try to build and develop for carbon removal needs to be able to achieve or contribute to remove like very, very large amounts of carbon from the atmosphere in order to be effective, because that's at the end of the day what we're trying to achieve: remove CO2 from the atmosphere, because all the climate models show us that in addition to very, very strong emission reduction, we will need to remove excess and legacy carbon on the order of like 5 to 10 gigatons per year, depending on which model you use. Currently, everybody knows we aren't exactly on the best track, so it's rather going to be on a pretty high volume and level. There's many ways to remove carbon from the atmosphere, but then we are looking for the ones that are like most effective. And I want to highlight some key features of effective carbon removal solutions. So what does that mean? First of all, a carbon removal solution to have an effect on the climate needs to be durable. And that means the carbon that you remove from the atmosphere needs to be stored for very long time frames, ideally millennia. So the background here is that emissions stay in the atmosphere for millennia, so removals need to match that. And there's like a recent paper, I'm not gonna go into this much in detail in my talk here today, but there's a recent paper out from my colleague Zeke, who just modeled a lot of the different climate scenarios and the impact that durability of removal solutions has on global temperatures. And it's like very evident that short-term removals can have like small impact in terms of like peak temperature, like you can probably achieve some peak shaving, but to overall like stabilize the climate, it's very critical that any carbon removed from the atmosphere stays so durably. So that basically puts us in looking for solutions that store CO2 in geologic formations as solid carbonates in the ocean bicarbonate buffer, or I mean, there's like some methods on how you can like render biomass inert, something like think of pickled biomass in anoxic basins, for example. Okay, the next thing for a carbon removal solution to be effective is it needs to be verifiable. That's kind of a no-brainer as well. We need to be able to measure that the effect that any activity has on the climate, right? So in the current market, or in the market that we are in today, which is very early and might shift in the future as well. But currently we sit in this model on a per ton basis accounting, right? So we are trying to, for any activity and carbon removal solution that's being developed, we try to verify the exact amount of carbon that's been removed to enable these market mechanisms, right? Like companies are paying for a certain amount of CDR that has been removed so that they can count it towards their net zero targets, similar as countries would do this. There's like multiple ways on how you can do this. For some technologies, it's pretty straightforward. If you have a direct air capture approach, you can directly measure the amount of CO2 that comes out in your pipe once you've captured it and it goes into storage. There's some considerations on like process emissions and your LCA to, calculate the overall net CO2 that's been removed. But there's like some methods where it's like a lot more fuzzy because it's not super straightforward to measure. We often talk about open system pathways. So for example, ocean alkalinity enhancement, but there's a lot of like activity in the field building out methodologies that can at a pretty high confidence level determine the amount of CDR that's happening as the result of an activity. Isometric here is an example of like a registry and protocol developer who's like working with a lot of suppliers. And then I also want to highlight the verification framework that we developed together with Carbon Plan that follows an uncertainty model where like every step in a process is attributed an uncertainty factor. And then there's like discounting happening to make sure we are staying on conservative side to not overcount any carbon removal and be, open-minded on like any leakage risks. And the idea is that with like better measurement and verification, those methodologies would advance in the future. And then the other two like really key considerations for any effective carbon removal solution, and that's why I want to really dig on deeper in today's talk, is scalability and cost efficiency. So again, this comes back to the sheer challenge scale that I highlighted at the beginning. For any carbon removal solution to be effective, it needs to scale to really, really immense volumes. And talking about gigatons and whatever, there isn't many solutions and there isn't many industries today that like move gigatons of materials. So this is really, really important. And it's not only that any solution needs to come to that scale, but it also needs to get there fast because, time is of the essence if we want to, stabilize today's climate. And then the scale also hinges on the cost, obviously, because it's very, very large scale, it'll be very expensive. So like any savings is going to have a big impact. If we're talking about like $100 per ton target, for example, that like DOE started to establish and a lot of others, including us, are kind of like using as a benchmark for high quality, high durability carbon removal. If you want to do 10 gigatons for $100 a ton, that means like about $1 trillion per year, which is, close to 1% of like global GDP, which is a lot of money. So the cheaper, the better, obviously. And then this also, like the cost, like one piece that feeds into it is co-benefits as well. So for like any solution, here, like if there's like valuable co-product or co-product revenue, or even if it's nothing that you can like monetize in today's industries and climate, there is obviously, if there's an additional value to any activity, it will help a lot with like social acceptance, social license support, which again like helps scalability and scaling speed, which is really, really critical for building these solutions. Okay, in this backdrop, I want to quickly introduce what we are doing at Frontier so that you understand where we are coming from, and like introduce some of the key work that we've been doing today. Frontier is an advanced market commitment, which is a market mechanism that's like borrowed from the health industry. Has been deployed very successfully, for example, for the pneumococcal vaccine, where buyers pooled together demand and said, if vaccines companies like start producing the vaccine, they will pay for it. And then this could like be deployed in like developing countries, helping a lot with the global health crisis there. And so similarly, we think this principle can be applied to carbon removal, where early stage technologies currently have like, limited demand to like build their solutions. So to really build this test bed for trial and error and like figuring out which solutions can work, we want to be like an early customer, signaling if you build solutions, we will buy, we will pay for it, so that we can all figure out what works and bring down these novel technologies, bring them down the cost curves as they scale. With that, so like funded in 2022, these are the founding members here. We have like pooled together over $1 billion to be spent on permanent carbon removal. How we do this is we pool the demand of all those buyers. So they have committed each a certain amount of carbon of money that they want to spend dedicated on permanent carbon removal. Frontier, my team and I will like sit in the middle, vetting different suppliers. So that's like people developing carbon removal solutions. And then we propose purchasing from these solutions and like facilitate the purchase between the buyer and the carbon remover. Importantly, the buyers aren't guaranteed like a certain amount of tons for their money commitment, basically for the volume of their commitment, which is like really critical for us to be as flexible as possible and like really choose the most promising solutions. We have like we purchase in two different what we call tracks. So one is like pre-purchase and one is offtake. They're like fundamentally extremely different. Pre-purchases is what we've done a lot in the very early years. And the idea here is like really to support like novel high risk solutions. There's like low volume purchases, typically to build from a first lab demo, the first of a kind like pilot or demonstration plant in the field, to really understand like performance in real world conditions and like really help this like scale up of novel technologies. And then offtakes are like, this is where the real volume is starting to happen. So these are like purchases on the order of like 20, 50, $70 million for approaches that are a little bit more proven and lower ecosystem risk, to really help companies get out, build first commercial plans, and get project financing and really start building large things. Again, this includes everything, importantly, like tech agnostic in a way, as long as our purchasing criteria are met, which I come to in a second. So direct air capture, enhanced rock weathering, bio oil injection, like all of everything is fair game if we think it can be effective again. And for most of these solutions, we're the first customer. We evaluate every carbon removal company across like 3 key areas. One is the approach, of course, like super critical. Do we think this technology is going to remove effectively carbon from the atmosphere? Is it scalable? Is it durable? Does it have a path to be cheap enough? Like all these things. Execution is also really important. This is a game of finding, or like in the purchasing, this is really also a commercial decision, right? So we need to be comfortable that teams that come to us are able to execute. This is like even more important for the offtake, obviously, where, you know, really large scale deployments are being proposed, and we need to make sure that the teams, you know, will be able to get critical partnerships in place and really deploy, which isn't trivial and is easier said than done. And then portfolios. So, you know, again, this is the decade to figure out what works. There's no silver bullet solution to this like really, really large scale problem in that volume. So it's likely going to be a combination of a lot of different approaches. So we hope to build a risk diverse portfolio, which will help build the most robust market to eventually get us to this like large scale solution with the biggest volume at the lowest price possible for carbon removal in the future. Okay, on approach, I touched on this before, like just really, really important. Again, the key criteria that we look for, permanence or durability, again, is really important for a number of reasons. And, you know, I really encourage you to check out Zeke's paper on this. Physical footprint, this comes back to scale. You know, we can't take up much arable land because we'll need it for a lot of other climate solutions. Costs I touched upon. Capacity, again, this comes again from the scale, and then there's a lot of other considerations. You know, net negativity is really important. If there's a lot of like process emissions involved, it makes a solution less effective. Additionality touches on like, would this happen anyways? If yes, we're probably not very catalytic, or it's not, you know, contributing to a net new carbon removal. So this is also really important. Verifiability I talked about. And then there's like social license and legality issues, governance issues. I don't want to gloss over that, but given this is more of a science audience and more of a science talks, I leave it at that. But it's like critically important to be able to scale these solutions. Okay, what have we done to date? In the past 2 years, we facilitated, or like almost 3 years now, 2.5, over 40 purchases. So we have like over 40 companies in our portfolio, 8 of which are offtakes, like large scale contracts, and we actually have like a lot more in the pipeline. The final contracting and deal closure is a very lengthy process, not to my liking, but okay. And then we have like 33 pre-purchases. Global portfolio, there's a lot of solutions in the US, which is a bit of a sign from like, I mean, multiple things. There's a lot of like government subsidies and just like a breeding ground for carbon removal solutions that probably has like started a little bit earlier versus in other parts of the world. But we, you know, see a lot of solutions come in from Europe and like all over the place. We hope to see way more being done in the global south specifically. And we're actively looking to increase global diversity, given that CDR is a, you know, global issue, obviously. Okay, the offtakes are like really, you know, big deal and like a novel thing to like really spur the market. Microsoft is another like really, really big carbon removal purchaser, in fact, like way bigger than Frontier. So I hope you know, see and hear a lot about these stories as well, because they do a lot in similar lines to help advance promising solutions. We've done this year alone 4 offtakes, and as I said before, we have a few more in the pipeline that are very close to announcement. I can't mention them today already, but I'm very excited. So keep your eyes peeled. Very different solutions. Vaulted, for example, $53 million deal of like waste slurry injections. So that's like waste that's like left from anaerobic digestion. There's like no value in that anymore. There's like PFAS contamination, and there's like currently this is typically landfilled. So there's like a lot of like issues with this type of waste and very limited or like no other use case for it. And by injecting it underground, you know, we can remove this biomass, prevent methane formation from it, and remove PFAS, for example, from like further downstream processes. Carbon Run, I'm going to talk to about more in a second too, which like really exciting first river alkalinity enhancement deal, which like feeds into ocean alkalinity enhancement. Super exciting to be closing that, and I'll talk a little bit more about that in a second. It's really important to start building these things. Obviously, you know, there's responsible deployment, and we do a lot to ensure these early projects are, you know, safe. There's ecosystem risk is like very limited. Monitoring is like extremely is done extremely well, but it's very, very critical to actually take novel technologies from the lab out in the field, because there's a lot of learnings you can only get in the field, right? You know, the impact of like weather, how does like your actually sourced feedstock behave versus what you've, you know, bought from Sigma Aldrich in the lab, right? So there's a lot of things, and it's like super important to be doing these things. And we and our suppliers and the field are learning a lot. We do a lot to encourage suppliers to make most of those findings public as well, to like really help grow the field. And I talk a little bit more about like ecosystem initiatives from us as well. Okay, project highlights. I picked just like two kind of random, so this two random but like exciting projects from our portfolio, and I picked projects that I think people probably haven't heard about so much, right? So I didn't pick direct air capture. I didn't pick enhanced rock weathering, which we've heard a lot about in the media last year. Hopefully you did, and that wasn't only in my bubble. Okay, so I want to highlight Banyu Carbon, which is a direct ocean removal solution. Very, very novel, very sciencey, like super sharp science team from the lab that developed this solution where CO2 is stripped from seawater and then can be geologically sequestered, can also go into utilization, of course. But the idea, you know, the atmosphere and the ocean are in equilibrium. So obviously you can either, for carbon removal, you can either remove CO2 from the atmosphere or as well from the upper hydrosphere, so from ocean water. And there's like multiple ways to do that. Banyu is looking into like a photoacid. This is like a chemical that if you shine light on it, it will release protons, so like acidify its environment and then relax back into its natural state once you remove the light source, right? And Banyu is developing a system where you pass ocean water by this photoacid so that when you shine light on it, the solution acidifies, which drops the pH below the solubility limit for CO2. So if it's like, if water is very acidic, CO2 will bubble out, given that it's a weak acid itself. So you can strip CO2 from the ocean water and then store it. This is pretty exciting because typically to strip CO2 from ocean water, you need quite a lot of energy. This photochemical system needs way less energy. And importantly, there's a concept that Banyu is evaluating right now where you can directly integrate it with behind the meter solar, so that like any solution built per se would actually be net energy producing, because you have like more energy from the solar panel that you need for your photo excitement of the acid. This is an example of like pretty early stage solution. There's a lot of like technical things to figure out, you know, your stability of the photoacid, how can you produce it at scale, like will supply chain, you know, be able to keep up with the timelines that we need. Is the overall process, once you pump your ocean water, filter your ocean water, whatever, is your economics still feasible? You know, like all the energy, if you account for all your entire process, is that still, you know, very attractive? Is the cost still attractive? So there's a lot of things still to figure out here. But I thought this is an interesting concept that people probably haven't seen. And then a second project I want to highlight is Carbon Run, also a water solution, but very, very different. This is a concept called river liming, which has been done in parts of like Canada and actually the Scandinavic regions as well, where rivers are strongly acidified from like acid rain and like industrial pollution, so that the water just in the river is like pretty acidic based to what it used to be in previous times. So by adding crushed limestone, which is just like calcium carbonate, or you can add that to the water, which is like alkaline, will raise the pH. And that has been done for like salmon and fish stock restoration in the past. But you can also extend this practice and not only do it to those 3 rivers where you want your salmon back, but you can, do it to all kinds of rivers that have like this chemistry where your limestone will dissolve, and you can raise the natural alkalinity of the river to levels where this alkalinity increase leads to additional drawdown, right? So important here, and stick with me on some chemistry, but I know we have a lot of chemists in the room. The basic principle behind this is, limestone is like calcium carbonate, and the alkalinity in the from the or the calcium ion basically is able, if dissolved in water, to balance 2 bicarbonate ions, versus if it's in solid state and bound with a carbonate, you have like only 1 CO2, basically your carbonate and your calcium. So by dissolving this limestone, you get an additional CO2 that you can balance from this reaction, which makes it a very attractive solution for carbon removal, because limestone is extremely abundant, very, very cheap to source. So this is an example of like an extremely low-tech solution where you just source limestone, you grind it up if you don't even have it ground up, because in many places it's actually finely ground stuff is like left from construction, which they don't use. So you can even source waste material. You can put it in the river, it like directly dissolves if the water chemistry is right, and you can measure your effective CDR pretty straightforward, even though it's an open system, by like measuring upstream and downstream of your deployment, and like measure alkalinity increase in dissolved inorganic carbon, and like a lot of other ecosystem parameters. So like super interesting solution, very low tech. This is coming close to bragging, but I was extremely happy this, like after this offtake announcement, and we had like a really big opening of the plant. The New York Times, literally covered on its title page a story about this like river liming solution. I think what's extremely attractive about it too is like the very tangible, real, and like very immediate ecosystem co-benefits, right? So by raising the river pH, natural ecosystems are restored, and literally, fish stocks are like back to what they were like 50 years ago immediately. So there's a lot of like community support, like yeah, it's a really strong story. And obviously, here you see my team. I took this picture of my teammates Judy and Zeke, and we were like very working on this deal for a very long time, and then to see a really positive article on this in the New York Times was just an amazing moment. So yeah, very fun. Okay. We purchase a lot of carbon removal. What else do? We do a lot, given that purchasing only isn't only what the market needs, right? So carbon removal is very early, and there's a lot of other things that Frontier is doing. Even, we don't do everything ourselves. We often like work with a lot of people in the ecosystem to like plant, seed, fund, help, and facilitate different ecosystem initiatives. And I want to highlight a few of those. The background here is that because of our purchasing over the past 2 years, we are sitting on a very, very big amount of data, and we also have a lot of expertise, because we talk to a lot of like academics, researchers, suppliers, politicians. We talk to so many people in the ecosystem, and it's like critical, we think, to like pull the threads together and like help build this web of a robust market. So one thing that I personally do a lot in my time in my role at Frontier as a science lead is building these foundational purchasing POVs. That stands for point of view POVs. So we build these like pathway POVs where we lay out, on direct air capture, what do we think, given all the things that we know, given the market, the uncertainties, all the different technological options and like sub-pathways, what do we think is a best approach to carbon removal? Should we do solid sorbents? Should we do liquid sorbents? Should we do electrochemical regeneration? What is the potential of all the different approaches? What are the different risks? How cheap do we think any of these can get? And then we bring all these paths, then we do the same for enhanced rock weathering, like what's the potential of like using olivine versus basalt, like what are the drawdowns from doing this in rice paddies versus, agricultural sugarcane fields in Brazil, what are all the different upsides and downsides, and then develop this point of view on what we think can build this most robust, biggest volume, cheapest carbon removal portfolio. And yeah, that's a lot of the work that we are doing. By doing that, we obviously uncover, given that the field is very early, there's a lot of open questions, and a lot of the work on the purchasing POVs revolves around like how can we purchase despite those uncertainties, right? There's a lot of like unknowns, things that are still open questions, and some for us are like, okay, this is like such a big risk, we don't know the ecosystem risk of this thing, so we think it's not ready for purchasing. Sometimes we see the need to like fill the risk, and then we launch initiatives to like try address and like fill this gap in the ecosystem. So here's like a few examples on biomass sourcing for bioenergy, for example. There's a lot of questions on like what's the best use case for biomass, and how do you avoid unsustainable biomass sourcing principles that would like negate or like work counter your CDR goals, right? And so we work with a lot of like suppliers and academics to develop these like sustainable biomass sourcing principles, to develop guardrails that we can pose up on suppliers to make sure sustainability is guaranteed and the bar is kept like really high here. For direct air capture, there's a big question, obviously, in the field. It's very energy intensive. How do we marry this, goal of scaling and starting to build these solutions to have direct air capture available in the future, while we still try to like decarbonize a lot of other industry sectors, right? Which we should, in a way, prioritize. And how do we avoid cannibalizing carbon-free, clean electricity from decarbonization efforts if we build out direct air capture? And we launched a study with like Jesse Jenkins' lab at Princeton to like develop similar like guidelines and principles, and like analyze like different scenarios for different strategies, because it's quite complicated in terms of like energy sourcing for these early industries. CDR ecosystem impact is another pretty big open question for a lot of different pathways, and we work with a lot of like academics and NGOs as well, like in the field, to develop like ecosystem impact metrics to be able to like evaluate suppliers and again give them guidelines on things that they should be measuring and looking out for. And then similar for measurement and verification, I already highlighted the uncertainty framework we developed with Carbon Plan, but then we also for example, worked a lot with like Cascade for enhanced rock weathering to build this like standardized measurement rubric, for example, for enhanced rock weathering, which was like really catalytic to enable like purchasing from this pathway. Okay, again, this is like examples on like things that we launched and did to help of the field, right? Like the carbon removal knowledge gaps database was like one of the first things I did in my job when I joined Frontier, a list highlighting research and innovation needs across all different technologies. The Carbon Removal Alliance is like a really, really big policy initiative. Like Frontier as like a commercial carbon removal buyer isn't always the best voice to drive a lot of political action. So we helped launch the Carbon Removal Alliance, which is, nonprofit organization building policy support and like doing a lot on the on that front across a lot of like carbon removal pathways. And then again, we do a lot of these like guiding principles for carbon removal buyers and others to help publish some of our thinking that basically comes out of the purchasing POVs that we build and like all these other documents and thought pieces where we try to highlight our thinking, how it crystallizes out from all the experiences that we have. Okay, I want to use the last couple of minutes here for to highlight a few key science questions that I see in the field. So I'm gonna flash up a heat map that might look like a lot to take in, but we will take a few minutes and talk through it. So don't worry. I want to say before I highlight, this isn't a comprehensive list, right? I'm totally omitting like any social license and governance gaps, which are like really, really big. And in general, I'm, stripping down and listing what I think are like currently the top unknowns or like research gaps for the individual pathways. Every pathway has a lot of like sub pathways, and they might not be fully matching up here for everything. So really high level picture, and the colors try to represent in a way, like if anything is red, this is like a very open question right now where I think there isn't a super clear path on like solving that, or there isn't been much done in the field. If something is green, it doesn't mean like it's of no concern, but it means mostly there's like lower concern, or it wouldn't really change how we think about this entire pathway, and also that critical initiatives are like underway to address this question. So with that in mind, let's just quickly talk through the different pathways, and then I want to highlight 3 very specific gaps and talk a little bit more about them. So for direct air capture and storage, lumping together all different approaches here, there's like some key open questions around the energy additionality. I already talked about this before. This is like, how do we avoid cannibalizing clean electricity that we need elsewhere? And like, how does this match with like overall scaling of direct air capture? The Wright's law assumption that I listed here comes to, how do we think about like coming down the cost curve and like cost and volume curves of like different technologies, right? Like and there's like some open questions on, we think we have a pretty good idea. I imagine like in literature, there's a lot of people that think they have a reasonable, like founded, informed view on what a cost down trajectory for like scaling of certain technologies is, but there's like some open questions, and if we are wrong on like certain things there, cost for direct air capture could be, much higher or lower. In terms of technology, there's like a few mineral looping direct air capture approaches where calcination, like carbon-free calcination or like low carbon calcination is like very critical, and currently that doesn't exist at scale. There's always questions on sorbent performance trade-offs. Like we see a lot of innovation around people developing novel sorbents, which have maybe a key performance metric, but then the question is always, how do you optimize that for cost at scale? And there's a lot of trade-offs to consider, which often, especially academic teams, don't super think of. Some open questions there. And then scalability of low TRL approaches. There's a lot of like very innovative, possibly promising ways to do CDR, to do direct air capture, but then scalability of like very custom and novel components that don't have supply chains today can be like a really big holdback. MRV is not such a big issue for geologic sequestration. Ecosystem risk also not the biggest concern overall for these approaches. Biomass, carbon removal and storage. availability of waste for CDR is like still a big question. You know, the role of like purpose-grown biomass. Where do we source biomass? How do we transport it? What are the best solutions for like different types of waste? And also, how will this develop in the future, right? So there's competing industries, some of which are like super important for climate. One could argue for SAF or, you know, other emerging technologies that utilize biomass. And the question is like, how does CDR slot in here? It's still a pretty open question. Some novel technology approaches, you know, next generation of gasification. Arbor, for example, is working on this. Thermal liquefaction, supercritical water oxidation. There's a lot of like novel processing methods, some of which have like co-value extraction, which is quite interesting. Some question on the MRV around durability, especially for like burial, biomass sinking, preservation technologies. And then some ecosystem risk around like nutrient removal, leakage of these like different storage methods, if that's not like geologic sequestration. Yeah, still open questions. On weathering, and I'm lumping together here enhanced rock weathering like in field, but also superficial mineralization, for example, of steel slag or mine tailings. So availability, location of feedstock is a question. Energy trade-offs between grinding and reaction rates, as well as like activation. So there's like some thermal or like chemical activation or bioactivation of, for example, mine tailings that are interesting. Microwave technologies, a lot of like different things that need to be figured out. Really big gap, that's why it's red here, is on weathering still around feedstock reaction rates. We do have, like for some approaches, quite a lot of data, like basalt in field weathering. We do have quite some data for like a lot of different feedstocks under a lot of different conditions. But there's quite a number of approaches in enhanced rock weathering where the data on actual feedstocks in environmental conditions is quite limited. And this is something I'm going to talk a little bit more in a minute. Some leakage concerns here on the MRV front that are still open or under investigation. And then for ecosystem, like especially for field weathering, interactions with soil organic carbon, some contaminations like trace metals, for example, in feedstocks, if spread on fields or in ocean, could be an issue. And then lastly, for ocean pathways, again, this is super high level overview. So I'm lumping a lot of like extremely diverse pathways here under oceans. Mostly focus on abiotic stuff, but still there's a lot of open questions given that this is a lot more novel pathway, but also the complexity is absolutely maximal in the ocean system where a lot of like biogeochemical interactions are going on. So overall, big open question still, is there a feedstock for mineral OAE that's reactive enough and safe enough and available enough to put into the ocean? This feeds again into like novel calcination tech, which is another important piece, because, you know, the ultimate goal or like the ultimate feedstock for ocean alkalinity enhancement would be lime, which you get from calcining limestone, which is very available and very cheap. But to do like that thermal process is very emission heavy. So the question is like, how feasible are low carbon calcination tech alternatives and what are the best ones, right? Is it electric calcination? Is it oxy-fired calcination? Should we be using rotary kilns? Or, you know, there's a lot of open questions. Low TRL approaches, hydrated carbonate minerals, bipolar membrane electrodialysis, some other electrochemical approaches, photolytic DOR, like I highlighted from Banyu. There's a lot of like really early stage stuff here. On the MRV front, again, feedstock reaction rates, specifically for mineral OAE, super open, big question, because we don't have good dissolution models for adding alkaline minerals to the ocean. And it's really, really tricky to measure. Air-sea gas exchange, lags, we're working with Seaworthy on advanced models here. Secondary precipitation, big question here, and like some ecosystem feedback loops around like biotic calcification and overall interactions with the ecosystem here. I'm getting wary of the time, so that was a lot to take in, I know. We're almost done. I wanted to highlight 3 gaps, but you know what? I want to discuss more, and I'm just going to highlight one. So I wanted to talk about novel calcination tech, feedstock reaction rates, and ecosystem feedback loops. I'll skip the calcination, the feedstock reaction. I'm going to spend 1 minute to talk about this, and then we're just going to have a discussion, and we can dig in anything we want. So for ecosystem feedback loops, one really, really big open question that I think not enough people are working on is this question of like adding alkalinity to the ocean. How effective is it really, right? Like we have near term like very, very good understanding of these things, but the question is, once we reach like very large scale, or we in specifically deployment locations, we will have a pretty high jump in alkalinity increase. Are there feedback loops that can reduce the effectiveness of this pathway? So both enhanced rock weathering, ocean alkalinity enhancement, river alkalinity enhancement, like a few other approaches, store CO2 in bicarbonate, like dissolved inorganic carbon in the ocean, balanced by the additional alkalinity. That's like durable, and we know oceanic bicarbonate, we can measure that, has been in the ocean or like has residence times that are like extremely high. But we also know, as I said, is a very complex system with like geochemical interactions. So the question is there any like unknown feedbacks to increasing the alkalinity that would, you know, interfere with our CDR? Is there something that we oversee right now with the current knowledge base? So, I mean, this could be good. It could be, you know, we have like more dissolved inorganic carbon available for photosynthesis, and like more microbes or phytoplankton or whatever are building up, and you have like just higher biomass pool in the ocean because you create like a better system there. But you also could shift phytoplankton communities, which could have like cascading effects. You could trigger biologic calcification or increase that, which releases CO2. So there's a lot of like interactions here that should receive more attention in the future, hopefully. So pointed out a few here that hopefully are addressed by some researchers. Okay, with that, I threw a lot in front of you, and it's always funny sitting in Zoom in front of a computer talking to a screen. So I'd love to talk to you really, and like have some questions and start a discussion. I wanted to highlight really quick, hoping that there's a lot of students in this talk right now. There's like 2 pretty cool initiatives in the ecosystem you should absolutely check out if you're a student. Inflection Award is awarding like high impact PhD projects. Applications close pretty soon, but please check that out if your PhD is focused on carbon removal or any other climate solution. Really cool project. And then the Carbon Removal Challenge is also like a really cool program for students where they are sent to New York Climate Week, and it's a really fun, great way to grow your network and get in touch with people working on climate solutions. So check that out if you're a student. And with that, thank you for your attention.